Hi everybody, my name is Stéphane Bégaudeau. I'm Sirius Web architect at Obeo. Today I will show you how to customize and extend the Sirius Web platform. For that, we will see how you can customize some features programmatically, then we will have a look at how to add a brand new kind of representation in Sirius Web. After that, we will see how you can export data in real time to synchronize Sirius Web with a remote service. And finally, you will see how you can integrate it inside of another application. So let's get started. First of all, a quick reminder about Sirius Web. So Sirius Web is everything you've liked in Sirius Desktop, but this time in a web browser. It comes with a graphical and domain-specific tooling. Everything can be defined using a configuration file, so you could use a ODesign file or you could define this configuration using the web browser. Everything is deployed on a web server and rendered using a modern web browser. It also comes with collaborative support, allowing you to work in real time with your colleagues. We also provide Obeo Studio, which comes with additional features on top of Sirius Web, such as authentication and authorization, the ability to create private projects, and role-based access controls, for example. You can also see the users who are manipulating the same representation as you do to work efficiently with your colleagues. Both Sirius Web and Obeo Studios are configurable with the concept of your domain. You can define graphical representation such as diagrams, forms, or even validation view. It's quite easy to get started by importing your existing Sirius Desktop configuration, your existing ODesign files with their Java services, for example. In lots of our examples, we are using the Flow Designer project, which works both on Sirius Desktop and Sirius Web. So, what's inside of the Sirius Web project? The Sirius Web project contains a ready-to-use modeling framework to define and render graphical applications in the web. You could embed this framework in other applications as you like. It also provides an open-source model server with various components that you can reuse. With this, you can build your own Sirius Web backend for your need. And on top of that, it provides a complete open source application offering tons of features such as diagrams, properties, forms. This allows us to integrate Sirius Web's components into existing web applications. Sirius Web relies on regular web technologies like Spring Boot, GraphQL, React, Apollo, XState, Material UI, to name a couple of them. It's very easy to find documentation about those technologies, and as such, it's very easy to contribute and extend the Sirius Web platform. In the Sirius Web ecosystem, you can find the Sirius Components project, which contains all the core components used by any application of this ecosystem. This is where most of the code related to the manipulation of data and representations is located: diagrams, forms, trees, and so on. It comes with both backend and front-end components to be integrated in a web application. Then we have Sirius Web, which is an example of the use of Sirius components. Most of the time when we are speaking about Sirius Web, we are talking about some code from Sirius components. The Sirius Web repository is way smaller than the Sirius components one. You also have the Obeo Cloud Platform ecosystem, which is based on both Sirius components and additional Obeo Cloud Platform components. Inside of the Obeo Cloud Platform ecosystem, you would retrieve applications such as Obeo Publication or Obeo Studio. You can build your very own application on top of Sirius components and be part of this ecosystem. So first, let's see how we can customize Sirius Web or even Obeo Studio using code. There are some features in Sirius Web that can only be configured using code. Most of those features should be available in a low-code or no-code approach in the future. For example, to customize the icons of your objects, you would have to modify the EMF edit code of your metamodel for those who are using EMF. You would use the same approach to change the child creation proposal available in the Explorer. You can also provide additional Java services to use them in your diagram description defined in the view DSL if you want to provide a very complex behavior for the tools of your diagram. You could also want to create the whole description of your representation from scratch in Java. I wouldn't recommend that unless you are a developer comfortable maintaining a Java application. So here you have an example where we contribute an additional Java service to use it inside of the expression of our diagram description. So we need to provide a Spring service or custom services provider, and it just needs to return the list of Java class which should be available when we want to manipulate a specific view. In this Java class, we have a getValue method, which will receive the semantic element on which it will be called and additional parameters. You can see at the bottom of the slide how we can use this Java method inside of an AQL expression after that. As I said before, you can create programmatically in Java from scratch your own representation description. So here I have a very simple example of a diagram description which is contributed programmatically. You just need to create a Spring configuration and add the representation description inside of the registry. Here we could connect easily our diagram description with any Java framework to help compute the appearance of nodes or edges and the behavior of our tools. Now let's see how we can add new features to Sirius Web. For this presentation, I've decided to add a new kind of representation which will communicate with a remote service. For that, I want to contribute it to our backend, describe it in our GraphQL API, and then integrate it in the front end of our application. After that, we will see how we can synchronize our data with a remote service. So for this presentation, I've decided to integrate a representation based on Google Maps. So this map-based representation will leverage the Google Map API to display the map. It will come with a dedicated metamodel to create elements with map-related attributes, GPS coordinates, and a zoom level. And it will also display the map and refresh it in real time when the object on which it has been created are modified. Okay, so let's start with the backend side first. We need to add support for this map representation. We need to describe how this representation behaves. We need to create the data structure of this representation. We need to make everything to support the creation of new instances of this representation. We need to provide an event processor. I'll talk more about that later, and to register it inside of our GraphQL API. So first of all, we'll create our new metamodel. To register a new metamodel in a Sirius Web application, you just need to create a configuration and provide the EMF ePackage as a bin. Here I've decided to create my metamodel programmatically, but you could also load an eCore file or reference generated code. Here my metamodel will only have one e-class with just 3 attributes for the GPS coordinates and the zoom level. After that, I can now create new instances of my map class. I will be able to edit the details of this object using the details view on the right, where I can edit the GPS coordinates and the zoom level. Now I want to add support for the map representation. I need to provide a description which needs at least an identifier and a label. I also need to provide a predicate telling Sirius components when instances of this representation can be created. Here I want to restrict this map representation to objects of my metamodel. I don't want to create this representation on any object in Sirius Web. I need to create the data structure of my representation, so I need an identifier, the identifier of its description, the identifier of the object on which the instance will be created, a label, and then I can add any data that are relevant to my representation. So here, GPS coordinates, zoom level. For a diagram, we have all the nodes, edges, and tons of other pieces of information. I need to register my representation description, just like the example I showed you before, where I registered diagram description created programmatically. I just need to put it inside of the representation description registry. Then I can start supporting the creation of map representation. So here I need to explain a couple of concepts. We will create an editing context event handler. The editing context is the container of all the semantic data. It's the unit of work, and it contains and isolates the data and representation from other editing contexts. Think about the editing context as a project in Sirius Web or a resource set for those who are familiar with EMF. Here, the editing context can receive some inputs, which are requests mostly coming from the front end, asking for operations to be performed. And in this event handler, we will first filter with the canhandle method the input to only consider input which are asking for the creation of a new map representation. Then we will create our map representation. We could use the semantic data to compute how this map would be created. We need to save it, and we will emit two events. The first one is a change description, which is an internal event used by Sirius component in order to find out if we need to refresh other representations, for example. So here we are creating a new representation. It may not be relevant to refresh, for example, other diagrams because it has no impact on those kind of representations. And then we need to use the payload sync to emit another event which will be used to respond to the HTTP request. So we have received an HTTP request asking for the creation of the representation. We will send back as a result that the representation has been successfully created. We also need to tell Jackson, which we are using for the JSON serialization, how to read our data structure. It's fairly easy. And after that, we can start creating map representation. So we can create it, it will appear in the Explorer, but we can't open it yet. If we try to click on it in the Explorer, the backend will just tell us that it doesn't know how to manipulate this representation and doesn't know what to do with it. So we need to dive a bit more inside of the architecture of the backend. In order to view a representation and to connect the front end to the lifecycle of the representation, we will need to subscribe to the events of this representation. For that, we will need to send a GraphQL request with a subscription, and to add support for our map representation, we will need to extend the GraphQL schema with a map.graphqls file, and to provide a new data feature which will allow users, the front end, for example, to subscribe to events of this map representation. All the lifecycle of the map representation will be handled by the MapEventProcessor. A representation event processor contains the representation, determine when the representation needs to be refreshed, is also responsible for the support of all the manipulation of the representation. For example, in the diagram event processor, all the tools that needs to be executed first arrive in the diagram event processor, which will determine what should be done. The representation event processors are contained by the editing context event processor, which represents the project, and it knows all the representation that are currently opened. And the editing context event processor registry is there is a single instance of the editing context event processor registry for the whole server, and it knows all the projects, all the editing context which are currently open and being manipulated by end users. To send the events when a map representation needs to be refreshed, the map event processor will use the map event flux to send those events to the GraphQL layer and thence to the front end. So first of all, we need to extend the GraphQL schema to add map related concept. So you can see that we have a map event field on the subscription, which can return a map event payload. That map event payload can be a map refreshed event payload, and the map refreshed event payload contains the map with the GPS coordinates. To connect the GraphQL layer with our collaborative code, we need the data fetcher, which will support those map events. It will receive the request from the front end asking to be subscribed to a specific map ID. And then using the editing context event processor registry, it will acquire the representation event processor and subscribe to its events. In the process, it will use the event processor factory, which will create in memory the event processor for the map representation. Its job is to ensure that we can really open the representation. The representation may have been deleted by another user in the meantime, so it will look in the database to find the existing representation, and once found, it will instantiate the map event processor using the current version of the map representation. And then we arrive in this key concept, the representation event processor. So inside of it, we will have this refresh method, which will receive all the change description and filter most of them to only consider those who are relevant to this map event processor. It will then refresh, save the new version of the map, and send it back to the front end to all those who are subscribed to this representation using the map event flux. In order to subscribe to those events, we have the getOutputEvents method, which allow the end user to subscribe to the map event flux. And when all the users will have closed their map representation tab in the front end, and then when the backend will know that there is nobody subscribed to this representation anymore, it will be disposed, and we can clean up everything in the dispose method. So thanks to this code, we can now provide a GraphQL API allowing end users, other applications, to subscribe to events of our map. Each time our semantic element will be modified, a new event will be sent with the new data structure of the map, the new GPS coordinates, the new zoom level. Once we have that, if we try to click on our map representation on the Explorer, it will just fail, because the front end this time will tell you that it doesn't know how to display this map. So we need to customize the front end. So on the front-end side, we need to register a new representation component using React. It will be used to define how to display the map. We need to register it on the entry point of the application, and inside of this component we can subscribe to those events using our GraphQL API. So here is our map representation components. It just needs to accept representation component props as an input. So here we have the editing context ID, the representation ID. It can also receive the current selection, for example. And then inside of this React component, you can do anything you want. So here we are using the Google Map React component. It's coming from an open source project I found on GitHub to integrate Google Map inside of React components. It just needs to get started GPS coordinate at the center of the map and a zoom level. And I'm also using a use subscription from Apollo client in order to subscribe to my flux of events from the backend. I need to define how I will be subscribed to those events. So here I have a very simple GraphQL request to ask for map refreshed events with the GPS coordinates and the zoom level. And inside of the use subscription, I only need the on subscription data callback, which will be executed each time the backend has emitted a new event. Here I filter for map refreshed event payload, retrieve the GPS coordinate, and update the state of my React component, which will in turn update the map. I need to register this new representation on the front end. So for that, we have the representation component registry, which is used by Sirius component to retrieve a React component for a given representation. So here, if the type of the representation is map, I want to display the map representation. If it's a diagram, I will use the diagram WebSocket container, which is the component used to display diagrams. Using this mechanism, you could also replace existing React component used to display diagrams or forms. If you want to display diagrams using another library, you could just keep all the backend code, but just change the implementation of the React component on the front end and interpret the diagram data structure that you would receive in a different way. And here you can see in the middle of the screen that we are using this registry inside of using the representation context provider to give access to Sirius component to our new representation. Once that is done, everything is connected and we can start playing with our map. So here we can enter the GPS coordinate of the Eiffel Tower or New York, and we can see our map move in real time. So let's have a look at a small demo. So here I have created a Sirius Web project. Inside I've created a map object and entered some GPS coordinates. If I open my map representation, you can see that we are in Canada, near Ottawa. I can change the GPS coordinate and the map is updated in real time. I could also update the zoom level and it would zoom, for example, on Liberty Island near New York. So now I have my custom representation using any JavaScript library you want, connected and synchronized with the data of Sirius Web. It can be used collaboratively. It works just like all the other representations. We could also improve this integration. For example, we could update the properties of the object, its GPS coordinates, when the map is modified. So we will only need to listen to changes in the coordinates or zoom level of the map. If you're zooming or moving inside of the Google Map canvas, then we would send a mutation to the backend. So we will need to extend the GraphQL API, declare that we are supporting mutations, and provide a data fetcher to handle those mutations. And when we will receive the mutation inside of the data fetcher, we can give it to the MapEventProcessor, which will be able to update the data, graphical data, semantic data inside of the MapEventProcessor, refresh the map, and send it back to the front end. And this way you would have something very similar to the way we are using tools in diagrams, for example. Okay, so now we have integrated a new kind of representation, but I also want to synchronize the data that are inside of Sirius Web with a remote service to be able to consume our data in another application. So here I have a very simple example in which I will publish and update a GIST on GitHub with the GPS coordinate each time I change the GPS coordinate in the Sirius Web. So for that, in the MapEventProcessor, when we are refreshing the representation, because we have received a change description telling us to update the map, for example, the data of the GPS coordinate have been modified in the object. After we have computed the new version of the map representation, we can create a new HTTP request and send it to a remote server. This way, the remote server can be synchronized with any change in this representation. We could also send semantic data at the same in the same method. In this code, we can also check to see if there are any differences with the previous version of the representation, for example, to not send anything to the remote service if there are no changes. We can perform the request asynchronously in order to improve the performances and lower the impact on the refresh of the map representation. And if you want, you can also synchronize data the other way. So you can make a remote service synchronize its data with Sirius Web. So for that, the remote service will need to send a GraphQL query to Sirius Web, and you will need to contribute an editing context event handler, just like we did before, to perform the change. In this handler, you can write pretty much anything you want in Java, and you would have access to the data. For those who are familiar with EMF, you can get access to the resource set and all the model objects, and you can do anything you want. So you could have a bidirectional synchronization with a remote service this way. And here you can see the result. Each time I change the GPS coordinate, a new commit occurs on the GIST. You can also integrate Sirius Web inside of other products. So what do we have in mind when we talk about integration? So you can integrate the Sirius Web model servers in other applications. You can consume HTTP, WebSocket API in front-end or back-end code in your application. You can also integrate any graphical representation provided by Sirius Web in your application, diagrams, forms, and so on. So to get started, you will need to integrate the Sirius components, front-end components in your front-end code if you want to integrate the front-end parts, and you will also need an instance of a Sirius Web server up and running somewhere, because we will consume its HTTP and WebSocket GraphQL API. In this example, we will integrate Sirius Web inside of a VS Code extension. So here you have an instance of VS Code, and VS Code is a very unique environment because everything on the left, so everything related to the data that you are manipulating on your file system and all the views that are provided on the left here are running on a Node.js process. On the other hand, all the editors, all the codes of the editors is running inside of a web view, and the code here is an HTML document running in a browser. So you have two different environments here, a backend one and a front-end one. So for the TreeView used to manipulate projects, for example, we are simply manipulating the GraphQL API over HTTP using Node.js, performing fetch request. That would be the same thing to integrate with Obeo Studio. So here you have an example of a fetch request in which we will retrieve the list of the projects available on the backend. For the Explorer, it's a bit different. We will display the model elements of the project inside of the VS Code. It will use the same definition of the Explorer as the Sirius Web one. It can be changed, it can be parameterized. It's a tree representation. So since it's a representation, it will be updated in real time, and we will need to use the GraphQL WebSocket protocol for that. So from our Node.js process, we can open a WebSocket connection and subscribe to the events of the Explorer to be refreshed when something occurs. This way, we can include Sirius Web data and react to changes to those data inside of our backend application, even for a desktop application. Inside of the web view of VS Code, we will integrate the front-end part of Sirius component to display a representation, here a diagram for example, and have it updated in real time each time something changes. So here we are creating the web view for VS Code, in which we are providing the code of our VS Code editor. And inside of this VS Code application for the web view, we can reuse existing Sirius component representation. So you can see here the diagram WebSocket container in action, which is the entry point to display diagrams in a web application. We just need to give it the identifier of the editing context, the identifier of the diagram representation we want to display, the current selection, and we can start interacting with the diagram. This diagram WebSocket container will then communicate with the Sirius Web backend, and it will be updated in real time. So using the debug tools from VS Code, you could see the GraphQL messages going from the front end to the back end and the back end to the front end each time you manipulate the VS Code application. It would also work in a similar fashion for the form representation. We could also integrate the map representation the same way inside of VS Code. So now you've seen how you can get started to integrate Sirius Web in your own application, backend or frontend. Thanks for attending this presentation. So if you want to try it, you can download Sirius Web from GitHub, and you have instruction on the main page to run it. You can then customize it with your concept, with your diagrams, to have your own modeling workbench. Now you know how you can add new representations. If you want, you can also use our hosted version, Obeo Studio, which comes with additional features. Thanks again for attending this presentation, and if you have any questions, don't hesitate. Thank you.
To warm up. Does Obeo Studio support Git integration?
No, we don't have a Git integration, but as I demonstrated it in my presentation, we could integrate any kind of remote service. So in the presentation, I demonstrated how you could call using HTTP request a remote service, but we could instead create a Git commit and push it to a remote Git repository, and we could synchronize the data inside of an instance of Sirius Web or Obeo Studio the other way around quite easily too.
Thanks for that. So next question. Sorry. Components probe. Are they required to implement custom representations?
No, that's a very good question. So we are using this React-like approach on the backend for our representations because it gives us the ability to more easily integrate common elements between representations. It's not required. I did not use that for this map example. It's just a regular Java Pojo that I've created manually just by doing new map. I don't have a renderer or anything like that.
Okay, thanks. Next one. Is the source code for the sample map representation available?
No, it's not available yet. I could publish it on GitHub. I will need to some parts first. But if you want to understand how a representation is connected inside of Sirius Web, I would advise you to have a look at the form representation, starting on the front end on form WebSocket container and on the back end with the form event processor. It's a more advanced example, but it's not as complex as a diagram one. And it's more, the code is more clean and mature than my quick example that I've created for this presentation.
Okay, and last question I have, but I think we can, take some more questions if you have, so feel free to ask, even if we are supposed to be just on time. What is the requirements on the database used by Sirius Web? Does Sirius Web provide such a database, or does it need to be connected to a specific deployed database?
So Sirius Web requires Postgres. I think that it may be compatible with other SQL implementation, maybe MySQL or something like that, but we have definitely not tested it. So I'm confident that it works only with Postgres, but it's not an hard dependency for Sirius components. Sirius components does not need to be connected to a database at all. You could make it work fully in memory if you want, and if you wanted to use a database, you could use any kind of database you need. You just need to define how you want to persist your data and how you want to retrieve those data.
Thanks. That and okay. Probably our last question. How much effort is it to integrate Sirius Web with other apps like WebPage, Jupyter Lab?
So I'm not familiar with the APIs and the lifecycle of Jupyter Lab, so I can't really answer that. What I can tell you is that to integrate Google Maps in the way I did, it took me a bit less than 1 day, but I know all the APIs of Sirius Component, and I knew exactly how to do it, so it was quite easy for me. I think that integrating with Sirius Web with a remote service, regardless of the service, if it has the proper API, could be done in a week to have a small proof of concept, and then it would take more time to to have advanced integration.